In this section of the course we will discuss an important topic which is focused on the response time of the sampling system. As we discussed before, we need to calculate this time to make sure it is within the accepted range for the application and the process, to take the corrective action in the appropriate time if needed. We also will learn more about Reynolds number and how it is calculated. And finally we will discuss the pressure drop that happened during transporting the sample through the sample line till it reaches the analyzer to make sure that the sample will reach the analyzer with the appropriate pressure for analysis. First we will discuss the sample transport time, or lag time. It is a function of the sample line length and diameter, the absolute pressure in the line, and the sample flow rate. Sample transport time is simply the total volume of the sample divided by the average flow rate in the sample line. For liquid sample, the sample volume is fixed and is the same as the volume of the sample line that transport the sample. For gas sample, a fixed quantity of gas, the volume varies directly with absolute temperature and inversely with absolute pressure. When we calculate lag time, there are some considerations that we have to take care of. Vaporizing a liquid sample can contribute to a severe lag time, because of the expansion effect of a hydrocarbon liquid changing into a vapor, 600 to 1, meaning that 1 cubic centimeter of liquid forming approximately 600 cubic centimeter of vapor. If we will have the vaporizer at the sample tap location, and since vapor speed loops may be only approximately 2000 cubic centimeter per minute, we have to minimize the liquid volume as much as possible to be able to purge the sample line with the new sample. Take care that partial vaporization might occur if the liquid volume flow is not sized properly for the vapor flow rate. To avoid the large dead volume, it may be advisable to drill a 1/8 inch hole through rod stock welded to a flange to use it as a sample probe. Also, as shown in this assembly, the filter and fittings are also low volume. If a tube between the sample vaporizer and the sample probe must be used, it is preferred to be of the smallest size possible. In this assembly 1/8 inch tube is used. All this is done to minimize the liquid volume before the vaporizer as much as possible and get a representative sample. Now, let us calculate the lag time. For liquid sample, the lag time is equal to the cross-section of the sample line multiplied by the line length. This gives us the total line volume, divided by the sample flow rate in the line. Note that the cross-section of the sample line is a function of the sample line inner diameter. This is dependent on the line size and the wall thickness. Also, to be more accurate, we consider the volume of the sample probe to get the complete volume of the line. In case of gas sample, and since gases are compressible, the volume of gas will vary depending on its pressure and temperature. So to calculate the lag time we will use the same equation as before, but the pressure and temperature should be compensated as shown in this equation. Take care of the following notes before using the equation. First, 10% allowance is taken in line length. For the pressure compensation, units are important. In this equation the pressure should be in psi gauge, then 14.7 is added to it to transform it to absolute pressure. If the pressure is given in absolute form we don't add the 14.7. If the pressure is given in bars we multiplied by 14.5 to convert it to psi. Also, temperature should be converted to Fahrenheit, which is equal to the temperature in Celsius plus 274.15, and finally the flow should be at standard conditions. Also note that if preconditioning pressure is less than the return pressure, sample pump will be required to prevent static flow. Now let us take some examples. In the first example, the phase of the sample is gas. Process temperature is given in Celsius, while the process pressure is given in bar absolute. The temperature doesn't change from the process to the return point, it is fixed at 30 degrees Celsius. The probe details are given, length and inner diameter. Line A is from the sample probe to the preconditioning panel. Note that its length is 0, meaning that there is no preconditioning panel in this case. Line B is 130 meter and its size is 1/4 tube and its inner diameter is 0.18 inch. Finally, the flow setting of the bypass flow meter and the analyzer flow meter is given in cubic centimeter per minute. The total flow is the summation of both flow meter settings. To calculate the lag time, we first calculate the total volume of the line. In this case we will calculate the inner volume of the sample probe, and line B volume, then add both of them to get the total volume. The volume is the area of a circle multiplied by the length. Area of a circle is pi multiplied by the radius squared. Note here that we multiplied the inner diameter of the sample probe by 2.54 to convert it from inch to centimeter, then we divided the diameter by 2 to get the radius. To get the total volume in centimeter cube, the length of the sample probe, which is in meters, is multiplied it by 100 to get it in centimeters, then we added 10% safety factor to the total length. We will do the same to calculate line B total volume, then we add the volume of the sample probe with the volume of line B to get the final sample volume. Now we can compensate in the equation to get the lag time. Note here that the total flow is divided by 60 to transform it to cc per second and to get the final lag time results in second. Also note that the pressure is multiplied by 14.5 to get it in psi, but we didn't add 14.7 because it is already in absolute, not gauge, so we don't need to add the 14.7. Finally, we added 274.15 to the 30 degrees Celsius to transform it to Fahrenheit. The final lag time in this example is 49 seconds, which is accepted. Let us take a more complicated example. In this example, we will have two sides, the side before the preconditioning system where the sample is in liquid phase, in the sample probe and line A. Then in the preconditioning system, a vaporizer transforms the sample to the gas phase, in line B till it reaches the analyzer. To confirm if this design is acceptable or we need to adjust to get a shorter lag time, we have different pressure and temperature in both sides. To calculate the lag time for this system, we will calculate the lag time for each side alone, then add the lag time of both sides to get the total lag time. So let us begin with the first side in the liquid phase. Same as before, we will calculate the probe volume, then the line volume. And finally add both volumes and divide by the estimated liquid flow to get the lag time in the liquid phase before the analyzer. Note here that even when using a short sample probe only 0.31 meter and the sample line between the sample probe and the analyzer is only 1 meter, the lag time calculated in the liquid part is 186.7 seconds. In order to decrease this time, we can use 1/8 inch tube instead of the 1/4 inch tube and shortening line A length as much as possible. The second step is to calculate the lag time in the gas phase. Same as the previous example, we calculate the line volume and then compensate in the equation to get the lag time, which is 20.64 seconds. The total lag time in this example is 186.7 plus 20.64 equal to 207.64 seconds. This time delay may be acceptable in some cases, or not acceptable in others. This is depending on the function of the analyzer, the cycle time of analysis and other factors, so we need to carefully consult with the process engineers to confirm if this design is acceptable or we need to adjust to get a shorter lag time.